guys for showing up. So didn't know what kind of a turnout we'd have, so it's good to see a few folks here. And for the sake of everybody, let's see, this is being recorded on WebEx, and we may later on post it to a website. So just to let you know, your comments, whatever you say goes through the speaker. It's all being recorded. We don't have a video camera in here, so it's only your voices that'll be recorded, and the presentation, of course. My name's Brent Sheets. I'm the research manager of the Alaska Center for Energy and Power. We had 3 wonderful interns down in Idaho, working at Idaho National Lab this summer, with the expressive purpose of looking at the nuclear technologies that are being developed for space propulsion for potential terrestrial application. And while they were down there, they met a fabulous other fellow who was on their team, Vishal Patel, who is also online, and he will be presenting from Idaho during a portion of this as well. I'm going to let our speakers introduce themselves and get out of the way. And those of you that are on the telephone, if you have trouble hearing anything, you should feel free to interrupt. And I don't know if there's a raise hand button on your WebEx or not. If there is, hit it, and Max will look for it, and we'll ask a question, or you can type your question in. Or if you feel comfortable at some point interrupting, I think you could probably do that too. But I think for the most part, we're trying to hold the questions for the end. Is that right?
Yeah, if we're going to do it at the end, but if there's something pressing, I mean, there's not enough of us in here to be too destructive. So throw something out if you have something on your mind.
All right, and with that, Mike, why don't you introduce yourself and the team? I'll sit down.
Great. First, Vishal, can you hear okay?
Yes, I can.
Okay, great. Vishal here is joining us from Idaho National Lab, Center for Space Nuclear Research, and he was a team leader in nuclear engineering for our project this summer. Alana, Vilagi, undergraduate in mechanical engineering here at the university, and she was our mechanical engineer for the project, and I'm Mike Kuca, and I'll be kind of hosting you through this real quick. So what we're looking at is the question of nuclear energy in Alaska. Really, it's the nuclear energy for remote applications. Bigger picture than Alaska. A lot of polar regions are considered here. So the objectives of this speech is we're going to consider the Generation 3 Plus and Generation 4 small and mini nuclear technologies for these remote applications. What we're going to do first is kind of talk big picture about technology. If you're not familiar with the topic, it's okay. We're going to start at the beginning and ease our way into the Gen 3 and Gen 4 areas. When we get to the Generation 4 technology, we're going to look at a couple examples that are paper reactors, what we call, and then we're going to take a little divergence into what our project was this summer with the Center for Space Nuclear Research and discuss the polar design. And that was a team of 6, 3 of us here talking to you, and the other 3, Haley, Taylor, and Christopher are not with us today. And then once we fully examine the Gen 3 Plus and Gen 4 technologies, we're going to really consider what the opportunities and obstacles are to a deployment in Alaska. Put it on a time frame, consider some things about policy and some economics. So the first big question that most people kind of address is, why are we even talking about nuclear energy in Alaska, right? Number one thing is cost and supply chain. So those 2 things together have an extremely high rate for fuel in remote locations. The first graph showed the road system, which was primarily the eastern side of the state. Now look at all the villages that are not serviced by the road system on the western side of the state. They're all serviced by barge for fuel generation. And the power generation that they have is predominantly diesel power generators. So that means that barge services diesel to all these remote communities and really accelerates the price of the consumer utility to well over $1 per kilowatt hour. And something we're not really going to get too deep into, but you're aware that power cost equalization with the state subsidizes that within these communities. The remote fuel prices can be driven up to $5 to $10 per gallon. So it's really quite a bit of precedent to say that the cost that the remote consumer is paying in Alaska is far, far greater than anything we see in the American grid. Second thing is the supply chain. As you're well aware, barges can only go when there's no river or sea ice. And our example of a disruptive supply chain here on the right is in fall 2011, there was an early Arctic storm that brought the sea ice unexpected. NOM hadn't received their fuel delivery yet. The ocean pretty much locked in, and we were unable to deliver NOM's winter fuel supply, which obviously was unacceptable. And after looking at the alternative of flying it in, which was just simply too costly, we sequestered Russia to send an ice breaker over to help deliver the fuel. So essentially, those are the two main reasons we're looking at the nuclear option for Alaska. Now, we're going to start talking about Generation 3+ and Generation 4 technologies for small and mini reactors. But let's go way back to the beginning. What do we mean by this? If you look at Gen 1, it's the early prototypes of the 50s and 60s. Kind of the transition from the solely military applications of nuclear energy, releasing it to the consumer market. In the late 60s and early 70s, there were improvements to the reactor vessels, there were improvements to the steam generators, and there was some passive design implemented, which kind of brought in the Generation 2 large-scale reactors. The fleet currently in this country is approximately 100 pressurized water and boiling water reactors in 31 states, and that generates approximately 20% of the nation's energy. So nuclear is definitely in our energy sector, and the predominant commercial reactor, which is a pressurized water reactor, is Generation 2. So the predominant of our fleet is Generation 2 pressurized water reactor with the complement of boiling water reactors. Now, for about 30 years after the 70s, there's been not really much talk of new nuclear construction in the U.S. And as some integrated passive designs were incorporated into the reactors, commercial reactor fleet, we kind of get to a Gen 3 area, and we're still on the large reactor scale, think gigawatt scale. And the differences between the Gen 2 and the Gen 3 and into the Gen 3 Plus really has a lot to do with decay heat removal from the vessel core. And what the Gen 3 Plus does is it takes passive design, allowing for the loss of power external to the reactor, and the coolant fluid, which is generally light water in these cases, is able to continue to moderate and remove the decay heat from the reactor core. Essentially, this is safety, passive design. We'll talk a bit more about that when we Gen 3 Plus is not on the market currently, but is emerging in the market. The first combined operating license from Nuclear Regulatory Commission was granted in the last couple of years for 4 new plants, 2 in Georgia and 2 in South Carolina. And those are the large-scale AP1000 that you see in the Gen 3 Plus section. Now, that's nuclear technology in the commercial sector, just big picture for the U.S. Now, we're taking that Gen 3 Plus technology, and we're looking at the small and the mini of that for Gen 3 Plus for the integral pressurized water reactor.
Wait, and can you just say how 3 and 3 Plus is different?
So Generation 3, there's an example here of the advanced boiling water reactor, and essentially the fine line between Generation 3 Plus and 3 and 3 Plus is a little debatable, but it's the ability to remove decay heat from the vessel core at the loss of power. Loss of power may be an example of earthquake, flood, whatever. If there's a forced convection system in the vessel, meaning that the coolant system is moving due to a pump, an external pump, if that pump fails, there's intrinsic design to continue to remove the decay heat from the reactor core for a period of time to ensure that it doesn't overheat the vessel at the loss of power.
So that's not the difference.
The second one, from 1 to 2, and again, you can kind of get 2 fine points on this. Some people may...
Could you repeat the questions for the folks on the phone?
Oh, absolutely. Vishal, we're having a question about the difference between Generation 2, 3, and 3 Plus.
Yeah, I think you're handling it well. It's semantics for the most part. The first generation reactors were literally the first ones made. The second generation used those lessons learned in the first reactors to kind of build safer systems. The Gen 3 ones are what you described, where you still have light water in your systems and they're still kind of building up on the Gen 1 and Gen 2. The biggest difference really is between Gen 3 and Gen 4. The Gen 4 reactors usually tend to not use the same kind of light water as your working fluid. And I think you were about to get to that, so I'll let you continue.
Okay. Thanks, Vishal. So when we're talking about the commercial nuclear fleet, we're essentially in the large and the gigawatt. So when we look at the Alaska energy sector, we really need to reduce that. Anything in the village is definitely less than 10, probably less than 5, maybe even less than 1 megawatt. So that's the village size. Generation 3, the difference with Generation 3 Plus did when any reactor is it takes an external steam generator so within the pressurized vessel, you have the external component of the larger reactor integrated into that vessel. That's the Generation 3 integrated pressurized water reactor. Again, it has extreme passive designs to remove decay heat. A couple of the examples that we're going to mention do not use any forced circulation at all. While they're normal operation, the decay heat is removed from the coolant. The most prominent ones in the U.S. is the Empower, that's Babcock and Wilcox, and NuScale, which is out of Oregon. Now, as far as maturity of technology, we believe we can say that NuScale is a little farther along because they have plans to develop a 16-modular unit in the desert west of Idaho Falls. And that is in the next 5 to 7 years. Those timelines, of course, are based on budget and cooperation, but NuScale's joined with Fluor Corporation to make that project happen, and it's fully funded by the Department of Energy for first-of-a-kind technologies. The Empower, as you see, is quite a bit larger. The numbers are in megawatt electric next to the reactor vessel. Quite a bit larger. There has been some events in the past 6 to 8 months where Babcock and Wilcox restructured their Empower division, and it's still yet to be seen how much they're going to make progress in the next, say, 3 to 5 years due to layoffs and budget cuts. But they are also funded by the Department of Energy for first-of-a-kind technology in small nuclear reactors. Now, we want to highlight 2 other reactors that are not U.S. reactors, because generally when you're talking about the nuclear reactors, the U.S. is generally kind of at the top, maybe the golden rule of the commercial reactors, but in the small reactor field, that's not necessarily going to be the case, because 2 reactors in the small integral pressurized water reactors are under construction now. One is currently in Argentina, that's the Kareem. That began with a 100-megawatt prototype, which was constructed and is in operation, and site clearing and construction on the 25-megawatt Kareem is expected in the 2017 to 2019 range. Russia is advancing the KLT-40S. That's a 10-megawatt reactor. It's actually 2 modules into one, so together it's 20 megawatts, and we're talking electric here. This is a really interesting reactor because it's actually mounted on a barge. The vessel itself has already been constructed, and there's varying reports on whether or not the reactors have been placed in the barge and placed in operation. But this is what they call a floating power plant, and they plan to be able, with this dual reactor system mounted on a barge, to go to any coastal region on a port and supply energy, heat, and desalinated water for a population up to 200,000. So that's as deep as we're going to get into those reactors in the foreign market, but be aware that they are competitive and in a lot of ways advancing beyond the American market. The Generation 4 reactors, which Vishal is about to get into detail on, they're advanced reactors in the sense that they use integrated designs, they use passive heat, decay, and et cetera, except their cooling fluid is often not a light water coolant. It's a gas coolant, a liquid metal coolant, something in the realm of molten salt, lead bismuth, or a pressurized gas vessel. And we're going to talk a bit more about that, but some of the most prominent ones, one that you may have heard about is the Toshiba 4S. That's a 10-megawatt electric reactor that was proposed for Galena in the 2010 range and before that. And there was even some talk about it making to permitting for the Nuclear Regulatory Commission, but that didn't seem to happen. That was a sodium fast reactor, and it's planned to be encapsulated and fully subterranean with a power station above the site. As we know, it didn't happen, but that's an example of a Gen 4 reactor. Other Gen 4 reactors, the lead bismuth cooled, the G4M, that's what we'll call a research reactor, or not research, but paper reactor, means that there's been a lot of research on it, there's been a lot of modeling, there's been a lot of executions in the academic, but nothing is in the production, there are no orders. The G4M is interesting because it's a, if you recall, in the 2010 range in the news miner, there was a talk about possibly having a reactor in Esther, and this was the model that they were considering. The investors locally didn't realize the time frame that they were looking at. Even today, we're looking at possibly 15 to 20 plus years before the Gen 4 technology is available. And that project didn't ever really even come off the ground. And then finally, a liquid metal fast reactor example is the STAR at 20. So what we're talking about here is the Gen 3 and Gen 3 Plus and Gen 4 reactors at a much smaller scale that are possible contenders for the remote market in the next decade and beyond. And with that, I'm going to pass this on to Vishal. Brent already kind of gave a brief introduction. Yes, sir, go ahead.
Are there any Toshiba 4S reactors?
In production? No, sir. As far as the Toshiba 4S, Japanese, there's been some, I guess, internal as far as the Japanese legislative and regulatory structure as far as pre-certifying that, but there is no construction, there are no orders.
Are there any small level reactors installed around the world?
Potentially, the one in Russia is, but the only caveat to that, and really to proprietary information in general, especially if it's associated with government proprietary, is we don't know exactly. They have published that the timeline for having that floating reactor in service is 2017. Whether or not the vessel is completed, whether or not the reactor is on site, don't know. The Kareem, the 100 megawatt prototype, just basically they build a larger prototype and evaluate the engineering, evaluate the data, and review it, and then they're constructing the 25 megawatt prototype that they plan to use as a small modular reactor. The 100 megawatt is constructed, is operated, and the 25 is under construction. So the only two activities in this field are in Russia and Argentina.
Just to add to that, there is a small HTR, high-temperature reactor being built in China, but it's still on the order of 100 megawatts, maybe 105 megawatts electric. So not small in terms of what we're trying to consider.
And that's correct. There is one good point to note here is that the IAEA says anything small reactor is under 300 megawatt electric. Pretty much kind of for what our considerations are for remote applications in Alaska, we're definitely under 50 and often under 10. And Brent already kind of discussed our collaboration, so I'm not going to belabor it, but Vishal, I'm going to go ahead and pass this on to you to discuss the Gen 4 reactor.
Sure, thank you. So the collaboration happened with the Center for Space Nuclear Research. The center, or the CSNR for short, the CSNR designs nuclear systems for space applications, and you'd ask yourself why are we in this kind of business of making a reactor for Alaska? So the environments where nuclear systems and space operate are usually very, very far away and also very, very cold. Alaska, especially rural locations, have similar, albeit much less harsh environments. And another big thing is that the communication time between the faraway space reactors and Earth is usually very long, so you can't do ground-based control very easily. So you'd have to design reactors that are fully autonomous. So there would be very, literally no maintenance required, and they would be able to provide power on their own without any human intervention. So reactors designed for Alaska should have very similar characteristics because you have a lot of problems getting to the reactors for maintaining them all year round, and you could have communications issues depending on different types of problems. So that gives us a good reason for the Center for Space Nuclear Research to be actually trying to design a reactor. So one of the big things that the CSNR is designing is the nuclear thermal rocket for space exploration. The nuclear core in a space reactor has to get very, very, very hot, on the order of 2,500 degrees Kelvin. 500 Kelvin. So the fuel that's used in the nuclear rocket must be able to withstand that type of high temperature. Because of this kind of idea, the Center for Space and Nuclear Research is designing a new type of a new fuel, which is a tungsten cermet fuel. It's a metallic and a ceramic, so it has the characteristics of being very, very high temperature with a very good thermal conductivity, which allows it to be a very, very safe fuel. And if you're going to try to introduce a new type of I'd say paper reactor into the environment where there's hundreds of reactors out there, you have to make sure that you're going to be very, very, very safe. So that's where we started from. We wanted to use that tungsten cermet fuel that's being designed for the nuclear thermal rockets at a much lower temperature and a much less harsh environment, so we can assure that we would have a very safe reactor during all times. We also wanted to make it very transportable. As you saw earlier, road systems are very difficult to transverse in Alaska, so you have to be able to travel by barge or by rail. We also wanted to make the reactor passively cooled and have a non-pressurized vessel just to increase the ideas of safety, as well as hit a power range around 10 megawatts electric or lower. The reason here is that the smaller grid structures in the rural villages of Alaska couldn't accept a reactor much larger than that, and probably not even 10 megawatts electric. Another thing is that there's very little reactor designs out there for this target range, so we thought we could be in a good little niche for that. We also wanted a very long lifetime because you don't want to do all the work of getting a nuclear reactor to location and having to come back and either maintain it every 12 months to refuel it or having to bring in a new whole module every time. So next slide, please. So the design we came up with is the polar reactor. It's a passively operated lead Arctic reactor. We designed for about 5 megawatts electric, which turned out to be about 15 megawatts thermal in our system. We have a lead bismuth cooled reactor with natural circulation. It's a very, very slow moving liquid, so it has a lot of kind of thermal inertia in it, so it could handle any type of loss of cooling accident. Essentially, if you lose cooling through your heat exchangers, the natural circulation in the lead bismuth coolant will be able to provide cooling to your core for a very, very long time. We're also looking at core outlet temperatures on the order of around 550 C. This allows us to use an open Brayton cycle at around 500 C. And the open Brayton cycle is really kind of neat in that you can use ambient air, compress it, run it into the reactor to heat it up, and then run that through a turbine, and then you'll have exhaust air through the turbine. The turbine makes electricity, and you have exhaust air, which potentially has a lot of energy still stored into it, so you could use it for other applications, or just put it into the atmosphere. This is really important because usually you'd need to have your reactor sited next to some type of cooling source, such as a lake or a river, and so this would allow us to not have to be necessarily next to one of those things. On the right is a concept view of the actual reactor we designed. The center in the blue is the actual core. You can see arrows that show the profiles of where the coolant would travel through. The coolant goes up the vessel, and then it gets cooled through the heat exchangers, and as it gets cooled, it has a higher density, so it starts flowing downwards, and then the reactor heats back up, and you get this kind of cooling loop set up. And on the bottom left is a concept view of what the turbo machinery for the air Brayton cycle would look like. Next slide, please. So another thing we wanted to look at was the lifetime of the reactor at 5 megawatts electric. We were able to do a lot of little tweakings in terms of core design for the tungsten cermet fuel, and the two designs we came up with had approximate lifetime about between 6 and 10 years. So that the 10-year lifetime turned out to be a pretty good point for us, but we also wanted to look at if we weren't tied to this tungsten cermet fuel, which by no means are we tied to this. It's just kind of the place we wanted to design from that really high safety kind of fuel perspective. So we looked at two different fuels that are being developed by the DOE right now as potential candidates for next generation reactor fuels. This is a silicon carbide fuel and a uranium zircide fuel. The silicon carbide fuel had a lifetime of about 5 years more, and the UZIRC had almost double the lifetime of the the tungsten ceramic core we designed. So this is essentially just telling us that we can design cores that can go longer and have similar characteristics. There's just going to be a trade-off in terms of, you know, how much safety and what performance you want in your actual reactor. So Alana will be talking about the actual uses of that process air that we can make if we didn't want to just create electricity, or as well as we wanted to do electricity and heat applications.
Right. So this summer, heat applications that would be the smaller heat load of an SMRS. And so some of the lower applications, such as district heating, greenhouses, fish processing, are all doable and all already being done throughout the world. And there's cases throughout literature for that. District heating, for example, has a long history throughout Europe as far as cogeneration with nuclear, and specifically Russia, who has a heating load that's higher for 7 months out of the year. Greenhouses are being built to be compatible with geothermal applications, and so why couldn't we use process heat from an SMR for this? And typically, if they're not using cogeneration, greenhouses use a boiler to produce the steam that they need. Fish processing or poultry processing can be used with cogeneration. One example of this, in Canada, there's Maple Lodge Farms is a poultry processing plant, and they've started using cogeneration to produce the steam and water that they need to process their chickens. Desalination has a variety of processes. That's why the temperature range is so wide. And there are plants that are using the heat off of test reactors for desalination processes. We were also asked to look at biomass to biofuels, oil production, coal to liquids processes, and possibly hydrogen production. These are all on the higher end of your heat loads. There's no reason that a core couldn't be run hotter and that the applications could be solely heat-based. So we could possibly reach these higher temperatures. Next slide. So this is just sort of a visual, and these are pictures from different examples, either throughout Alaska or throughout the world. The first three are Alaska. The second one is our greenhouse. The third is an example I wanted to bring up. So Akutan, and correct me if I'm saying this village name wrong, is looking at district heating as a possibility in their village. So they're looking to see if they can develop the infrastructure, and this could be a great test site. The fourth picture is a desalination plant in Trombay, India, that uses their reactor from the school. So with biomass to biofuels, right now the issue is while we can reach the heat needed and the temperatures needed for these processes, combustion still proves to be more efficient and is generally simpler than the process that we would need to go through for process heat to be applicable to this. That fifth picture is the Alberta oil sands, and the Toshiba 4S, when it was first being talked about, has been cited as a feasible reactor for this application. I guess I'll hand it off to Mike to finish us off.
Okay, so those were basically, you have some real opportunities to the nuclear power plants, the small and mini nuclear power plants, both electric and heat. And we have a really proven technology from multiple vendors, multiple national labs. So really, what are the obstacles to bringing this type of technology to market? And we want to talk about policy and economics. So number one, the easiest way to think of the current structure of the Nuclear Regulatory Commission is that their licensing process has been molded to the pressurized water reactor fleet of the commercial reactors in the U.S. Therefore, that mold is easy to somewhat replicate with the integral pressurized water reactor. The IPWR, the Gen 3 IPWR, is essentially a cousin of the pressurized water reactor because it takes a lot of the same engineering, a lot of the same concepts, and integrates that steam generator. So in order to get licensing for IPWR, you're much easier to go through that pressurized water reactor mold of the Nuclear Regulatory Commission to reach the goal of a design certification. They have staffing and core damage frequencies that are incremental to the light water design. Now, when you start talking about the Generation 4 reactor, you're talking about a different coolant. You're talking about different data, different engineering statuses, and as Vishal was talking about, a different fuel potential. So these do not fit nicely into that pressurized water reactor mold of the NRC. And essentially, you really have to create a new licensing process. So what your options are is to take the existing mold and try to have new regulations, which is time-consuming, exemptions, which can be really complex when the design starts to change, or risk-informed performance-based licensing. And that's what we're going to get more into, is that's referring to really changing the mode of the NRC regulation for the Generation 4 advanced reactors. The next generation nuclear plant project was happening in the mid-2000s, between 2000 and 2010, and funding for that is not currently flowing from the DOE, and the project is not currently ongoing, but they did look carefully about developing the certification for reactor technology of Gen 4. And essentially what the IPWRs are planning to do is use the same core damage frequency model that the large-scale reactors are using, but the Gen 4 would really need a new metric, and the new metric is proposed as dose exposure to the public. And this really highlights a lot of intricate design differences between the IPWR and the Generation 4, saying that the IPWR is likely to use the existing mold of the NRC with a few exceptions, but the Generation 4 would need a whole new model of regulatory process. This gives a good timeline of kind of wrapping it up, what we're talking about, the Gen 3 Plus and the Gen 4. The earliest estimates for anything Gen 3 Plus is with NuScale in the desert west of Idaho Falls, and that's going to be in definitely the late 20-teens to early 2020s. A lot of estimates are placing the IPWR Gen 3 reactor, Gen 3 Plus reactor in the time frame of 2022 to 2025 to be in the commercial market for Alaska. When you start looking at the Generation 4, you push that out probably another decade. So we're looking at possibly 15 plus years guaranteed before anything Gen 4 really happens. And really one big challenge with the Gen 4 reactor is not only the mold, the regulatory process that they have to go through, but the NRC wants them to take an additional risk-informed performance base and run through two licensing processes at the same time, which is essentially double the money in licensing processes. Licensing processes are not cheap. It can do up to half the capital of the reactor itself, in the hundreds of millions of dollars, sometimes over $500 million. So really, as all these things are developing, especially with the Generation 4 ideas with Toshiba proposed for Galena, Alaska decided it was really time to take a look at their structures from the legislative side and say, you know, what do we have? What does it mean? And the Alaska Sustainable Energy Act of 2010 is also known as the Omnibus Energy Bill of 2010. And it essentially had the result of putting nuclear on a level playing field with other alternative technologies. All the alternative technologies essentially are based on economics. And previous legislature had said that the nuclear option for Alaska was based on health and safety, but they felt that that was a dual representation of the NRC, because the NRC's goal is to regulate the health and safety from the reactor design, the operation, and any kind of public exposure. So Alaska essentially rewrote their stature on the possibility of advanced nuclear reactor technology in the state by the Omnibus Energy Bill, and said that anything they consider will be based on economics. They gave the executive had the power of siting for a nuclear site. That was taken from the executive and placed in the legislature. That means the Alaska Congress now has the ability to essentially select and move forward with siting as far as new nuclear reactors go. The DEC was tasked with external regulatory processes that don't include the EPA and the NRC. And that would like any energy project that would include fish and game, water, conservation, anything that the state needs to add on to the existing federal regulations. Note that neither the legislator or the state in the form of DEC has done anything to advance this beyond the Omnibus Energy Bill of 2010. Further, their last language in that legislature said that the municipality for which this project would be proposed would have to agree and be on board. So, big picture, with the considerations of Generation 3 Plus and Generation 4 nuclear technology, we recognize that Gen 3 Plus is the most advanced, most mature of this integral light water technology. And we do expect by the DOE funding, by the vendor activity, and by planned construction projects that this will be likely on the market in the realm of 2025. And we know from past literature and past experiences that we've seen in the Alaska media that the Alaska market is going to be targeted for this type of technology. And we believe that it's really up to Alaska, especially the University of Alaska and collaborating partners, to continue the research and development into this technology. Because if our infrastructure and our understanding of the technology is not prepared, when the commercial marketing comes in and targets this technology, I think we need to really keep current on the situation to make educated decisions. A big point to make about the lower 48 first-of-a-kind energy technology is it's almost always associated with a super utility, meaning a large utility focusing on large capital utility. Alaska doesn't have anything of that. And if this technology were to proceed in place of a super utility, we'd have to have an alliance of the stakeholders. Now, simply speaking, the stakeholders in Alaska are military, civilian, and industry. There has been discussion on all levels, industrial, military, and civilian. We gave the example of the 4S and the G4M in Galena and Esther. Those were discussions with the civilian. From the military point of view, they already have had a reactor operating at Fort Greely in the 1960s through the Army Nuclear Power Program. And their uses of district heat and need for remote applications running off of diesel generators is pretty big, so they are candidates for this technology. And finally, industry. When we talk about remote industry, especially something in the example of Red Dog Mine, which is completely off the road system, completely dependent on diesel generations, they may become candidates as stakeholders as well. It would take several entities of stakeholders moving forward to really take the place of a super utility. There are licensing challenges, as we pointed out, for the Gen 3 Plus, but they're not insurmountable. The state could consider looking at early site permitting, which would consider feasible sites for this technology. In addition to that, it would execute the legislator ability to begin the site permitting process. And as far as economics, it's always a big catch when you talk about this technology, because the large capital is always up front. What you get on the back end is you get in the IPWR example, is a 60-year vessel with 2 to 3 year fuel cycles. That means that your supply chain and your costs are really regulated and focused down into something that the energy sector can manage. But funding that first-of-a-kind capital up front is always very big. We've seen from the examples of DOE that they are willing to fund this technology and are actively engaged in delivering Generation 3 Plus technology by 2020. This was the legislative words of the Energy Policy Act of 2005 and the greater executive and legislative intent of national intent to be energy independent by 2020. Now, we know we're not going to hit the 2020 mark, but just from the federal point of view, the funding and the initiative is there as well. So those are kind of the big pictures of where we could be going with Alaska. I just want to give you an idea on the references. We won't make any specific mentions, but this isn't just a what we did this summer project. This is a real emerging energy technology that's going to be available for the energy sector probably in the mid-2020s. And we really believe Alaska is in the candidacy for being marketed to. And with that, we're going to open it up for questions.
And if there's questions in the room, would you be sure also to repeat it?
Hey, this is Ron Fabish from the NRC Commission.
Great, Ron. Go ahead with your question.
Yeah, question. Not a question, maybe a comment and a question. So I've attended this licensing Reactor licensing workshop last week here in DC, and it was attended by someone from INL as well. Was it? I think it was John something.
It was actually, Ron, that was Haley McIntyre, and she's in class right now.
No, it wasn't Haley. It was a guy. It was John. I can have his name somewhere. Anyway, it was Inzi maybe? From Idaho.
Yeah, the only one from our team was Haley that was in those calls, so I'm not sure who you're referring to.
Yeah.
You know, just a little bit of background there. Probably aware of this too, and folks, there's a lot of background on the microphone, so if you're not, it'd be great if you mute it. But the reactor was originally a concept that was originated at the Idaho National Lab early on, and then Idaho didn't pursue it, or the Department of Energy, or the Atomic Energy Commission at the time didn't pursue it, but Japan kept that technology alive, and that 4S technology came back through Toshiba. So Idaho's always had a real interest in the Toshiba reactor.
The name of the person is Jim Kinsey. Do you know Jim Kinsey?
No, we don't.
Okay,
Haley actually worked with Jim Kinsey over here, learning more about that licensing procedure.
Okay, so Jim Kinsey is from your lab. Anyways, so he was there, and he's involved with the NGMP project quite a bit. Apparently, he's the lead at Idaho on NGMP and the licensing issues that came along with that. But my message is that we can build on the existing mechanisms within the NRC Part 50 and 52, and specifically to Part 50 that has the two-stage for licensing. It has a lot of exemption possibilities that fast reactors or any advanced reactors can kind of use in cutting the time that it will require for the analysis. What I gather is the main limitation is the staffing at NRC of expertise in advanced reactors per se, in terms of the systems, the safety systems per se. And I think that's surmountable, like what you say, it's not insurmountable. And if we do not try to reinvent the wheel, in my opinion, on licensing, then it's just a matter of someone who wants to build one of these to go to the NRC commissioners and say, we need your licensing procedure to start. Or the processes to start, and it's a chicken and an egg argument that people are having, but I think that it's really not a huge obstacle, and so I agree with your final conclusion, but I really think that creating a whole new rule at the NRC will take more time and more money than we might want, so that's my message on that.
That's great, Ron, and for the benefit of everybody here, Ron Fabish is a nuclear research fellow from Argonne National Lab, who's on fellowship to the Senate Energy Committee, where he deals with energy policy issues for the Senate Energy Committee. And Ron was going to be here in person for this presentation, but his trip was postponed until probably the first or second week of December. So we might have another opportunity to invite Ron here for maybe even a seminar if I can talk him into it. So we'll see.
Yeah, I mean, there's a lot of my message maybe to you guys in overall. I'm really happy with this presentation. I'm really happy with the activities on advanced reactors and solutions for Alaska, and which is something that Senator Markovsky, as you know, is very interested in. I think that the message is that it is very doable, and I think that it's just a matter of getting those the issue of economics resolved. As you say, that's probably the most important issue for Alaska.
Great. Thank you. Okay. Moving on, any other folks who have questions?
Oh, I'm sorry.
This is David. I have a question.
Go ahead.
This is David Lockard at the Alaska Energy Authority. I was kind of intrigued by the references to the Galena proposal that has been a topic in Alaska for quite a few years now. And I just opened up our PCE report on Galena. Last year they paid $3.70 a gallon for fuel, and their average load was about 600 kilowatts. Of course, the thermal load there would be much greater than the electrical load, but I was wondering if there were any comments on whether that, environment with less than $4 a gallon fuel and 600 kilowatt average electrical load, combined with the flood they had last summer, if that changes the perspective on the prospects for Galena as a potential site.
Well, I'll speak to you as an opinion. Obviously, I don't have any authority to speak to the Galena project, but when the Air Force closed down Galena, I think that greatly limited the project in that area because of the decline in fuel and energy consumption. I think if you wanted to kind of get back into what is possible in Alaska, what's feasible, I think we would be talking about obviously the Gen 3 Plus reactor, which is looking right now like NuScale is the most mature, although that's just an appearance right now. But that's at 35 megawatt range. So we'd probably be looking something more, if we're talking about villages, something more like Bethel that had a greater demand and potentially as a energy hub. As far as proposing any specific village like Galena or any technology, I think we're going to have to talk about something on a larger scale until the Gen 4 is available for the commercial market, and then we can start looking at things smaller than 10 megawatts.
Thank you.
I have a question. This is Ron again. At this last slide, you talk about the master limited partnership. So it's something that I pretty much talk about also in my presentations on SMR. Have you explored this in more details for Alaska?
In certain detail. I mean, obviously, probably as you're well aware, is that the MLP has certain tax advantages for energy investments.
Right.
And that's what makes it so appealing when investments start becoming returns on investment, those tax advantages become very appealing. So the main point, I guess, we have here as far as the MLP, it's associated with the alliance and the fact that there's no super utility. So from an economic perspective, if Alaska, let's say the technology was available today and we were determining if we could do it or not, economics is a primary hindrance upon that, and the way to achieve that with the lack of a super utility is to get something in the realm of a University of Alaska and Department of Defense joint operation or joint efforts to realize this technology while simultaneously encouraging the formation of an MLP that can contribute to the capital funding of the first-of-a-kind project.
The question on MLP stems from the fact that on the federal level, as far as I understand, in terms of the tax code, MLPs cannot be done for nuclear energy, and any actually for renewables neither. It's only for oil and gas, piping especially, and that was the genesis of the MLP. It's really for oil and gas industry. So I was wondering if this was a state-based kind of tax scheme. I'm not sure what the MLP, how you view the MLP mechanism.
Absolutely. Everything you said is correct, and it would take a state legislative act or a federal legislative act from the Senate Energy Committee to either update the 510 or, I guess.
Actually, it's the finance committee or the budget committee, I think, will do it. I think budget. So it's not even in our purview, I think, in our committee. But regardless, yeah, it would take a legislative action to change that, and that's something that I'm a firm believer in, and others as well. Other senators, other members, I think, have been looking at it too. I think Senator Coons has been looking at it. But regardless, I thought that there was some type of a state-based mechanism for some arrangements like this, but it sounds like there isn't.
No, as far as I'm aware, it would definitely take a legislative change to restructure tax code as far as the MLP is concerned for investors on emerging energy.
Okay, thanks.
No, I see. Yes.
How long? So the polar unit requires compressed air to be run through it. You said it will run for a long time without compressed air, but how long?
Could you repeat the question?
Yeah, it's not air. I'm actually going to give this one to Vishal. You want to know how long it could run, or?
Right, because I mean that would be the thing that would be the security issue, right?
So if your question is if you lose the air cooling, if you lose the cooling capacity, what happens?
Okay. So Vishal, the question's on decay heat, and if you, I guess we need to explain, like, if maybe for a incident or intrinsic incident, how would the decay heat continue to be removed from the?
I would call that a loss of heat exchanger or loss of kind of cooling ability accident. Essentially, we did look into that, where we essentially set the heat transfer from the heat exchangers to 0, and we turned the reactor off. So we followed a typical decay heat curve that you'd see. Essentially, in a few seconds, your power level decays down to about 7%, and we looked at how long we could actually mitigate that decay heat, and we found that the thermal inertia that's stored in the lead bismuth, as well as still the ability to do some natural circulation at that lower power density, you can essentially be able to air cool the outside vessel and still keep the reactor cool for as long as you wanted.
Could you go to slide 10 for a second? I think I had a question on slide 10. So this is how long before you have to replace the core. And you guys, years.
Yeah. So I'm just going to grab this, Vishal, real quick, and see if you want to jump in. Go ahead, Francis.
So my question relates kind of like to what David was asking a bit ago, which is related to the economics. What would the overall cost of replacing the core be relative to the initial capital cost, or how does that compare? I imagine that's...
You're actually asking a really great question, okay? And the question is it refers to the design of Generation 4 reactor as compared to the 3+. The 3+ reactor is designed for a vessel life of 60 years, but the fuel is replaced every 2 to 3 years. So that's one unit, refuelable unit. Most of the Generation 4 units are factory sealed units that operate for the life of the fuel, and then that reactor would be essentially returned to the manufacturer. For decommissioning, the potentials obviously would be reconditioning and refueling, or scrapping it and decommissioning it, etc.
But would be a nuclear battery would be a poor description of it. But.
Yeah, that's a word that's used. I was told not to,
Right.
but that was one of the words that are used. But the real cusp of what you're asking is really integral to the discussion of technology that would be available. If you talk about something that you want out in a remote village, I don't know if you want a refueling cycle. You might want a sealed nuclear device that generates energy for 10 plus years, et cetera. If it was more on the rail belt type of frame, something, the integral pressurized water reactor, a vessel life for 60 years with 2 to 3 year fuel cycle, if you had the infrastructure to facilitate that fuel rotation, then that would be key. Beyond that is the economics. Okay, a large reactor, a gigawatt reactor that's producing a lot of energy and particularly selling a lot of energy over the period of its life is arguably economically on that same level, in the 10 cents to 15 cents kind of kilowatt hour that you might see in the lower 48 markets. Now, these intrinsically, especially the Gen 4, we're looking at some increased costs because it's first-of-a-kind technology. And we did some careful cost estimates on it, and we kind of concluded that right around the 10-year mark is where we need to be, 10 years and greater, to have a return on our capital investment. And essentially, we've discovered it's pretty straightforward that if you're going to reduce the power that you're going to sell by a magnitude, you have to extend the life of the reactor in order to reclaim your capital investment. You could have a shorter life with a higher magnitude of energy, but you can't have a short life and a low power and expect to reclaim a capital investment on this type of device.
That's 10 years is assuming life cost.
Repeat the question.
Yeah, they're asking about the cost of electricity, and the kind of guiding rule in this discussion is called the levelized cost of electricity, LCOE, very commonly used in all energy technologies, not this one particular. And we believe that a breakthrough cost for off the rail belt is at 40 cents per kilowatt hour. And the reason we believe that is because examples of power cost equalization, this is a quote from 2010, so it's a little bit dated. But from 2000 to 2010, the power cost equalization paid in excess of $200+ million for subsidies for energy. And one example here is Bethel, in that 2010 year range, essentially had a cost from producing the energy at 64 cents per kilowatt hour. And the state covered half of that at 32, and the consumer paid half at 32. Real similar actually to what Dr. Favish was talking about the tax code, is that the power cost equalization only applies to oil or diesel generation. It doesn't apply to emerging energy technologies. So you could not expect to insert something at 40 cents per kilowatt hour and then assume the customer's going to pay 32 and the state's going to pay 8. You can't assume that because it's not a hydrocarbon technology. And a lot of tax codes exemptions, a lot of other cost exemptions like the power cost equalization and subsidy, it's delivered specifically to the hydrocarbon combustion. But so there's an exception to that with the PCE. What I'm saying is you can't expect them, but we believe if we can have anything in the range of 40 cents per kilowatt hour, it becomes very marketable to the remote Alaska market. Any other questions?
This is David. Could I speak to that last statement?
Yeah, absolutely.
I think the PCE policy is a little more nuanced than you indicated there. For example, at Tizimina, they provide more than 80%, maybe more than 90% of their power with hydropower. This is on Lake Iliamna Non-Dalton New Haven Electric Cooperative, and they get PCE there. So it's not quite as black and white as you indicated. But I would also suggest that the cost of nuclear power should be compared to the cost of the fuel that goes into the diesel plant in most Alaskan villages. And 40 cents a kilowatt hour fuel cost is approximately equal to about $6 a gallon fuel, maybe five to six. And so the non-fuel costs of administering and insuring and managing, maintaining the distribution system and the rest of the electrical utility would still be there.
Very good. All right, 1:30. Anybody have any final comments or questions? Seeing none in the room. Anybody on the phone? No? Let's give our speakers a round of applause. I appreciate that.
Thanks for joining us, and Vishal, thanks for contributing.
That's great.
Yeah, thanks for having me.
Okay, well, thank you all very much. See you.
Okay, thanks a lot for inviting others. Talk to you later.
Okay. Yep, thanks, Tom. Bye.
That's it.